All right, welcome to The Explainer. Today is all about the ultimate Java interview cram session. No fluff, no filler, just the stuff you absolutely have to know. We're going to move quick, so buckle up.
So, you've got a Java interview coming up, right? Or maybe a big exam? Perfect. We're about to dive into the key questions that really separate someone who knows their stuff from someone who's just guessing. First up, let's look at what's going on under the hood. Okay, Section 1, Java's core engine. We've got to start here. This is all about how Java actually runs. What makes Java, Java? And here we go. First question up. What is the difference between the JDK and the JRE? This is probably one of the first questions you'll get. It's a fundamental check. Do you know what you need to build an app versus what you need to just run one?
Okay, so it really just boils down to this. The JDK, that's the Java Development Kit. Think of it as the entire toolbox. It's for building Java apps. It has everything, the compiler, the debuggers, and importantly, it includes the JRE. Now, the JRE, the Java Runtime Environment, that's just the essential stuff you need to run a Java app. It's got the JVM and the basic libraries. So here's the easy way to remember it. The JDK is the whole car factory, but the JRE is just the engine and the gas you need to make the car go. All right, next up. How does Java pull off its most famous trick? You know the one. Write once, run anywhere. How is it possible that the exact same code can run on Windows, a Mac, and a Linux machine without you changing a single thing? Well, the secret sauce is this two-step process. First, you write your code in a standard .java file. That gets compiled, but not into machine code for a specific computer. No, it gets compiled into something called bytecode. You can think of this bytecode as a kind of universal intermediate language. And then, this is the crucial part, the Java Virtual Machine, the JVM, that's installed on your specific operating system takes over. The JVM for Windows knows how to translate that universal bytecode into something Windows understands. The JVM on a Mac does the same for Mac OS. So that JVM, that is the magic translator that makes write once, run anywhere a reality. Okay, so now we know how Java runs. Let's shift gears and talk about how Java is designed. This brings us to Section 2, the OOP blueprint. We're talking about the 4 core principles of object-oriented programming. This is the absolute foundation for writing good Java code. And here they are: abstraction, encapsulation, inheritance, and polymorphism. These are the 4 pillars. You have to know them. And trust me, they're not just fancy buzzwords for an interview. They're the ideas that make your code clean, reusable, and honestly, a lot easier to manage. So let's hit them one by one. First up is abstraction. Honestly, this is all about hiding complexity. It's about showing only what's necessary. The best analogy is a car's remote. You press unlock and the car unlocks. You don't need to know about the radio frequencies, the security codes, the internal wiring, none of that. You just need to know the button to press. That's abstraction. In Java, we do this with abstract classes and interfaces. We hide the messy details and just show the simple controls. Next, we've got encapsulation. The name kind of gives it away, right? It's like putting your data and the methods that work on that data inside a protective capsule, which, in Java, is a class. The whole point is to guard that data. You don't want other random parts of the program reaching in and changing things unexpectedly. It's a huge deal for writing code that's both secure and predictable. Then there's inheritance. This one is all about code reuse. It's a lifesaver. Think about it. If you have a vehicle class and then you want to make a car class, well, a car is a vehicle, right? So instead of rewriting all the code for has wheels or has an engine, the car class just inherits all of that from the vehicle class. It lets you build on top of code that's already written and tested. Super efficient. And the last pillar is polymorphism. It's a big word that just means many forms. And what it lets us do is super powerful. It means you can have different objects that respond to the same message in their own unique way. For example, you could have a dog object and a cat object. If you tell both of them to make sound, the dog will bark and the cat will meow. Same instruction, different behaviors. This is done using method overriding and overloading, which we'll actually touch on again in a minute. Okay, let's move on. Section 3, memory, specifically stack versus heap. This is a big one. When an interviewer asks about this, they're digging deeper. They want to see if you really understand where your data lives and where it dies. So here's the classic question. Where does Java store simple variables versus its objects? The answer involves two very different places in memory, the stack and the heap. They couldn't be more different in how they work.
Let's break it down. The stack is all about speed and short-term memory. It's where your method calls and local variables go. It's super fast and works on a last-in, first-out basis, which means as soon as a method is done, poof, all its memory is automatically cleared. Super efficient. The heap, though, is a completely different beast. This is where your objects live. It's a big, wide-open space designed for things that need to stick around longer. It's slower to access, and it's not automatic. You need the garbage collector process to come around and clean up old, unused objects. So think, stack is for temporary, fast stuff. Heap is for long-lived objects. All right, section 4 is all about essential keywords. Think of this as a rapid-fire round. These are the little building blocks of Java logic, and you can bet an interviewer is going to want to know if you understand the subtle differences between them. And let's start with a classic mix-up. Method overloading versus method overriding. So many people get these backwards, but nailing this shows you really get polymorphism. The key is knowing where it happens. It's actually pretty simple when you break it down. Overloading happens in the same class. You have two or more methods with the exact same name, but they have different parameters. It's just a way to have one method name do slightly different things. Overriding, on the other hand, happens in a subclass. This is when a child class takes a method it got from its parent and provides a brand new implementation. Same name, same parameters, but in a child class.
Okay, here's a great one that tests your deeper knowledge. Why are string objects immutable in Java? Meaning, once you create a string, why can't you change it? It sounds like a limitation, but there are some really powerful reasons behind this design choice. The big thing to remember is that immutability is a feature, not a bug. First, it makes strings automatically thread safe. If multiple threads are reading a string, you never have to worry about one of them changing it. It also boosts security for the same reason. But the really big win is performance. Because strings can't change, Java can do something clever called string pooling. If you have the word hello 100 times in your code, Java just stores it once in memory and has all 100 references point to that one spot. That saves a ton of memory. All right, we're on the home stretch. Section 5, concurrency and error handling. Now we're getting into some more advanced stuff. But these are absolutely critical concepts for building applications that can handle the real world. Apps that are tough, reliable, and can do more than one thing at a time.
Let's talk about threads. Imagine you have a bunch of threads all waiting in line for something. How do you tell them it's their turn? Well, you have two options, notify all and notify all. If you use notify all, you wake up just one single thread from the line. The problem? You don't know which one. It's up to the system. But if you use notify all, you wake up everybody. They all get up and then have to compete to see who gets the resource next. And even though it sounds like more work, notify all is usually the safer bet because it guarantees you won't accidentally leave an important thread waiting forever.
And what about when things go wrong? An error, an exception, what happens then? That's where the finally block comes in. Think of it as your ultimate safety net. The code inside a finally block is guaranteed to run. It doesn't matter if the code succeeded or if it crashed and burned with an exception. It will run. This makes it the absolute perfect, non-negotiable place to put your cleanup code, like closing a file or a network connection, so you never ever leak resources. So there you have it. You've got the concepts, you know the what and the why, the core engine, the OOP blueprint, the memory layout, all the big stuff. The knowledge is all there. Now the only real question is, what are you going to go build with it?